And it is now my pleasure to welcome Daniel Polin from UC Davis and the Rubin Observatory. And he is going to speak about the systematic effects from low Earth orbit satellites on the Vera-C Rubin LSST.
Hi, I'm Dan Polin, and I work on the Vera Rubin Observatory camera. So we're going to transition from radio astronomy to optical astronomy, and specifically to survey astronomy. So survey astronomy isn't just looking at one target, it's looking at large swaths of the sky. And so Rubin Observatory, which you may know better as the LSST, is an up-and-coming survey that's going to take a picture of the entire night sky every 3 nights. We're going to image the entire southern night sky to the depth of the Hubble Deep Field over 10 years. And we're going to get great data on how the sky changes from day to day as we're taking continuous data. So to do this, we built the largest digital camera ever made. We're going to take 2,000 images per night, constant 15-second exposures, and that's about 20 to 30 terabytes of data a night. On the right here, I have a mock-up of the field of view of the telescope. And for comparison, I put how big the moon would look on that, and how big the proposed ELT field of view would be, and how big the JWST's largest instrument is. So as you can see, it's a much different animal than these small target telescopes. And because we have such a large field of view, about 10 square degrees, we're going to see a lot more satellites. We're a lot more impacted than most target telescopes. So first I want to talk about how number of satellites scales with the impact on our survey. So first is if you have about 1,000 satellites, less than 5,000 really, we can probably avoid them. So on the right I'm showing what the average image would look like. Whenever there's a satellite going by, if we have perfect information on where they are, we can just move to somewhere else and take an image there. As you get towards the 10,000 or 40,000 satellite range, avoidance becomes impossible. It's just not economical to try and move the telescope. You lose more data moving than you do just imaging and deleting those pixels. So this is about the number of satellites at various times that's been thrown out for like 1 or 2 satellite constellations. So we're almost certainly going to get to this many satellites. That's about 1 streak per image on average, and it goes through about 13 of our CCDs, so the segmented detectors. When you get to the 400,000 satellite range, that's, if you look at the total number of FCC filings, it's somewhere in the 300,000, 400,000 range. You're going to get 10 streaks per image or 100 on the horizon, and that's obviously a much greater impact to our survey. We would prefer if that didn't happen. So now we're going to look at one of the detectors in our focal plane. So the focal plane is made up of 189 of these smaller detectors. If you look at just one of them, then we can see the impacts in the individual scale. So each one of these is made up of 16 amplifiers, which are all read out simultaneously through different cabling. And we need to do this in order to read out the whole camera in 2 seconds. If it was just one big detector, it would take a couple hours to read out the whole thing, and that's obviously not very good if we want to take an exposure every 15 seconds. So each one of these small detectors is a 16 megapixel detector on its own, each CCD. And this is what I like to call a real image of a simulated streak. So this was taken in a laboratory using our real detector. Using real optics that simulate the LSST seeing, but it is a simulated mask that looks like a satellite streak. So basically we're able to simulate the effects on the actual camera due to satellites. So obviously there's the direct issue, which is we lose pixel area. Whenever a streak goes by, we just have to delete all those pixels. They're not usable. The streaks are something like 100 million times brighter than the objects we're looking for in the night sky, so it's very difficult to work with. And so we need to mask out those pixels, and we need to obviously detect where they are in the first place. Those present problems on their own, and if you want to hear more about that, I recommend going to see Adam Snyder's poster, which is more informative. But there's also, you can see this ringing effect where you don't just get the central streak, you get these other streaks in adjacent amplifiers. And the reason for that is because there's coupling between the different amplifiers and the cabling coming out. So you get something like a much less bright streak each segment over. It's a factor of 10 to the 4 smaller. So we need to be able to calibrate that out. And in order to do that, we need to be able to know how it scales for a certain brightness. And unfortunately, it seems like this is scaling non-linearly. But we need to do that for all of our amplifiers. And for each amplifier pair, there's about 23,000 amplifier pairs, so it's a lot of data that's needed to do this. So this is the most technical graph in my talk. It's a graph of nonlinear crosstalk versus intensity. So on the y-axis, I have a crosstalk coefficient. That's the ratio between how bright the crosstalk streak is, the response streak, and the central actual satellite streak. And as you see on the x-axis, we scale the brightness of the central streak. As you scale that up, the ratio is not constant, which means our crosstalk is nonlinear. This is just 8 different amplifiers, and we need about 3 parameters for each amplifier pair. And as I said, there's 23,000 amplifier pairs. That's something like 5 million observations we need to do in order to calibrate this out on the whole camera. Fortunately, we think we'll probably be able to do that on the month time scale because we take a lot of data with this thing. So now instead of number versus impact, I want to talk about just how brightness of the satellite scales with the impact. So we're going to first say what we want, the error on our system, and then say how bright that means the satellite is. So if we want to be able to correct crosstalk, let's say, to less than 10% error, that means that we need a peak streak brightness of no more than 5,000 peak electron count, which is somewhere in the 7 to 8th magnitude range. This calculation is dependent on a lot of things I put up there, which I don't have time to go over, but if you want to look at the slides online, you can read more about that. So at this point, faint science is going to be affected. So things like looking for asteroids on the horizon, world-ending asteroids, that's going to be more difficult to do, or things like trying to map out the dark matter in the universe. That's one of the central goals of our telescope. So that's going to be more difficult to do with the crosstalk reduction from this. You probably can't even see the crosstalk in the projection here, but it's barely visible, even with this scaled plot. So then instead, if we want to say we want less than 20% error, that's something like a 10,000 peak electron count. Now we're in the 6th to 7th magnitude range. So that is, for comparison, that's the edge of where you can visually see is things brighter than 6th magnitude in a dark site you can see. Things fainter you probably can't, unless you have really good eyes. So at this point, many of our science programs are going to be affected. Things like we're going to get a lot of false alerts in our system for any transients. Because our main goal is to map out the whole sky and the changes in it, so we're going to get a lot of false flags, and that's when we start to actually impact our survey a lot. So beyond that is when our CCD starts to saturate, which means it can't take in any more electrons for a given pixel. So this is quote-unquote correctable, but how trustworthy is your data if it has more and more error? So that's somewhere in the 100,000 electron range, which is somewhere around the 4th magnitude. And at that point, most of our science programs will be affected. So we really hope that we don't get that bright. If we can keep it in the 6th to 7th magnitude range or fainter, that's optimal. And then beyond that is when the electrons start to flow over into adjacent pixels, so they fill up the whole CCD. This is a blooming effect where the entire CCD becomes basically useless. There's no data there anymore. It's all ones. And we hope that we think that the CCDs are resilient enough to handle events like this on some repeatability. So this is somewhere in the 0 to 1st magnitude range. That's something like the AST Blue Walker is already that bright. So we really want to avoid having satellites this bright. We especially want to avoid having satellites, in the 10,000 number range that bright. So this is a demonstration of if we had a 0 to first magnitude satellite streak through our image. If we had 40,000, this would be the average image, and that would be about 7% of our survey lost. So that is bad. So the takeaways from my talk are really nothing new. Survey astronomy is particularly impacted because we have a large field of view. We're looking at the whole sky. Rubin Observatory is just one large example of this, and hopefully there will be more in the future. The fewer satellites, the better. Less than 10,000 is optimal. I would say less than 5,000, but we're past that point. 400,000 is kind of untenable. We're getting to the point where we lose more data than it's really worth to start making surveys, potentially. And then fainter than visible to the naked eye is necessary to have the type of error that is usable for most things and to not get a bunch of alerts that make our survey really bogged down. So that's my talk. Thank you for having me.
Thank you very much. We have time for one question, perhaps. There's several. Okay. And you're always free to grab the speakers at the coffee break and post your question on Slack. But could you state who you are, please?
It's Paul Daniels, UK Federation of Astronomical Societies. If you have a saturating satellite pass through your field of view, how likely is it that it will carry over into the following image?
Pretty unlikely. We do persistence tests on these detectors, and it seems like there isn't very much of a ghost on the next images. I don't have exact numbers for the answer for that, but small. We don't think it's an issue.
Okay, maybe time for one more question, if there was one more.
Dylan, I was wondering if the radar cross-section of the satellites that pass over scales pretty well with the brightness that you observe in your images? As in like the cross-section size of the satellite?
Right.
Yeah.
So obviously all of these things are dependent on the profile of the satellites. Yeah, there is a scaling with the profile of the actual satellite to how big the streak is. Adam Snyder does a lot of work on that. He's sitting 2 seats in front of you. So I recommend talking to him over the break.
Okay, thank you very much, Daniel. Let's thank the speaker again for the excellent talk.